lecture. So, welcome to this second lecture in Geographic Information Systems and Water Resources. Today we're going to cover the first exercise, and there's two parts to this exercise. The first part is a refresh on working with ArcGIS Pro, and the second part is building a watershed base map. I'm going to leave the first part for you guys to do by yourself, and I'll be working through the second part, which is a set of step-by-step instructions for building a watershed base map. I should just point out a few things related to the course. If I go to Canvas here, you'll see under announcements, I will typically the day of or the day before post the material, the material for the day's lecture, which in this case just links to the exercise, as well as the go-to-meeting connection. Under pages is where the material will build up. So there's material for Tuesday's lecture and today's lecture. And under the material for Tuesday's lecture, you can see the recording. So that's where there's a link to YouTube, and you can go back and watch that. And the lecture's being recorded, and as you shortly afterwards, I've got a file that I have to convert to MP4 and then upload it to YouTube. So any questions on that? So in terms of turning it in, you'll notice as you work through this exercise, it says in italics periodically to turn in a PDF document for part 1 with the map layout generated at the end of that exercise. So if you work through this exercise that's linked here in ArcGIS, or that's links to learn.arcgis.com, you should be able to construct this map, create a title with your name on it, work out the deforestation saved, and put in a real number there, and then upload the PDF, and that'll be what's used. If you work through this part here, you'll see similarly there's italics scattered throughout, and then right at the end, there's a summary of the things that you need to turn in. So there's a summary that for part 1, that's a repeat of what I just read to you, and there's 4 different parts for part 2. And I'm noting here, so make one PDF document for part 1. I said a separate single PDF document, so that's for part 2 should be a separate document, either PDF or word processor document, with the answers to all 4 of those embedded in it, and uploaded so that I can have a look at your work. I'm also expecting to get from you today some answers to the first assignment that I called assignment 0, which was really your pre-assessment of the knowledge and for you to tell me a bit about yourself. So I'll be looking for that tomorrow. So let's go back to this. I'm going to move this to half screen, and most of the time I'm not going to be referring to it because we'll have ArcGIS occupying the full screen. But this exercise says it's intended for you to build a base data set of geographic information for a watershed using the Little Bear Logan watershed as an example. If in doing this you prefer to do this for a watershed where you live, you are welcome to do that. It'll be a little bit harder because you'd have to identify it yourself. And I've actually provided here data for 3 stream gauges in the Logan Little Bear watershed, and you'd have to do that for yourself. But that's not too hard. So feel free to do that if you want, or you can just follow the instructions directly. The first thing we need to do is open the national map. We'll be getting all of the data we need from the national map. So there I've opened the national map viewer, and the first thing we do is we want to hone in a little bit towards the area where we're interested in, which is northeastern Utah. There is the Logan River and Utah State University. And we're going to be working with the NHDPlus data. So I'm going to click on hydrography here, click on NHDPlus high resolution, and we're going to work with a USGS 4-digit region, subregion. So I'm going to click on that. And now this, I found that this thing used to spin quite a lot while I was doing that. So not worrying about that, I immediately clicked on find products, and it'll do the search, and it'll find the products that meet the filters that I've set based on the area that I've got displayed. So it's selected just a few things. The first one is the one that we actually want. That's the high resolution National Hydrography Dataset Plus for the region 1601, which is the one that I actually know. 1602 is to the south, and I think 1704 is up in Idaho. So what we're just going to do is download the vector data. We're only going to work with the vector data, not the raster data for this exercise. So if I click on download that, it says it's going to be saving an NHDPlus GDB zip file. So click save on that. That download might take a while, so I will leave it to download in the browser there. In the meantime, I'm going to start ArcGIS and create a blank map document. So if you're following along on the exercise, we're on page 3, and we start ArcGIS by clicking on the Start menu. I actually have a shortcut that I've put on my taskbar, but I'll show you how you get it. Normally, you can find there's an ArcGIS group there, ArcGIS Pro. If I just click on that, it'll launch the software. And the first thing we do is we're going to need to pick the type of project that we want to work with. And we're going to work with a map. So I'll click the blank template map. And now it says to create a new project, I get to choose where I want to put it in my computer, and I get to give it a name. So I'm not going to put it in that default location because I've chosen to organize things a little bit differently. I've got a documents folder on my computer, and I've got an ArcGIS work folder within that. So I'm going to say I want that folder, and I'm going to call this the base map project. I guess I'm calling it base map exercise. If I follow the instructions and I say OK, and so now it's creating that project. In the meantime, I'm going to switch to my file system, and there is the ArcGIS work folder. You'll see that I've got a few other things in there already. I've got a copy of the geodatabase downloaded in case the download took too long, and some other work I've been doing, the preparation for this exercise, the Rondonia Amazon exercise. But this is the folder that just got created. You can see the time is 3:09 p.m. today, and that has in it a GDB folder, the project file, that's where the information about the project will be kept, and some other files that the system uses. So ArcGIS tends to generate a lot of files on the computer, and they will all be in this well, they'll mostly be in this folder, and if you need to move things around, if you move this folder to a different location or even to a different computer, you can, but maintain the relative locations of things, it will continue to work. So now, in the meantime, it looks like my file download has finished. I can see that from my browser. So I actually get downloads onto my desktop. So there's the file that we just downloaded. I'm going to copy that and move that into this base map exercise folder, and I'm going to unzip it. So I'm just going to extract it to this location, and you'll see that there were a few new files added. There's this folder NHDPlus _H_1601 HUC4 GDB. That's the geodatabase. There's a JPEG file, an XML file, and the original zip file. It's best to not work with ArcGIS folders or files directly in the file system, but always interact with them in ArcGIS, because if you change the locations of one of these files or delete one of them, then things tend to break. So I'm going to switch back to ArcGIS, and this is where I'll be doing the majority of my work. So I can expand this little panel at the right is called a pane, and whereas this I'm referring to it as the main window, and then on the left I refer to this as contents. And there's a number of objects here, but the first one I'm going to open is folders that shows effectively looks in at my folders, and there's one created for base map exercise. That's the one where we're doing our work. And if I open that, eventually it will get itself organized. And you'll see there's the base map exercise GDB. There's this NHDPlus GDB that we just unzipped. And there's a toolbox, and then there's the JPEG file and XML file that we also saw that came out of the zip file. So I'm going to now expand this NHDPlus data that we got from the national map, and I'm going to work with WBD. That's the watershed boundary dataset. We're going to work with that first. So I'm going to expand that, and you can see here there's WBD-H2, 4, 6, 8, and so on. So those are the watershed boundaries of the different hierarchies we're dealing with. What we're going to do here is identify the single HUC8 watershed that is the one we're interested in, and use that to effectively define the boundary of our watershed. And then we're going to download the HUC12 watersheds, which splits it into smaller pieces. If you actually look in this data set, you'll find that 14 and 16 are empty. Those are there just for completeness, but this data hasn't been filled out for this area yet. So I can add in content from a file that I've downloaded here into my map just by dragging. So I take this WDB-H8 and just drag and drop it on the map. And it says it's adding data there. So now I'm on page 6, and you see that it's displayed this set of 6 polygons, and it actually zoomed in on that area. So rather than seeing the whole US, now we're zoomed in on the northern Utah region. I might want to actually just see these as polygon outlines. So I can adjust the symbology, and the way I do this is click there to modify the symbol. You'll see that what appears on the right is the format polygon symbol tool, and there's a symbology tab that appeared at the bottom that I can switch back and forth between the catalog and that. And I'm going to go with a fairly bold outline. So I'm going to click this black outline that's fairly bold. And I'm also going to change the color by switching to properties and picking something like a green rather than a black. And then if I click apply, so now I've got polygons of the 6 HUC8 regions in this HUC4 watershed. I guess technically the term is 6 HUC8 subbasins in a HUC4 subregion, I guess it is. And I can click on one of them and a little pop-up will come and tell me about it. So I see, if I pop up that one, I see that that's actually the Little Bear Logan. This one there is the Middle Bear. This one is the Bear Lake one. We're going to focus on the Little Bear Logan one that has the identifier 160100203. And you can see there's various attributes associated with it, an area in square kilometers, an area in acres, and then there's a shape length and a shape area. And those numbers look a little bit puzzling, and that's because they are actually calculated using latitude and longitude as length quantities, and that doesn't actually make a lot of sense. So we'll see later on, once we've pulled this into our own geodatabase, how we can get the shape length in more meaningful quantities. So to do that, we're going to basically use a feature data set to organize all our information. I'm going to switch back to catalog, and I'm going to go to our base map geodatabase, which if I expand it right there, it doesn't have anything into it because this was just a blank map that we opened. And if I say right click and say that I want a new feature data set, this will be effectively a container for all of the information that we want, and it's going to have a specific coordinate system that we choose. So when I do that, you see in the pane on the right, the geoprocessing tab opens. A lot of work in ArcGIS was done with geoprocessing tabs. And within that, there's the Create Feature Dataset tool. And you can see that whatever I do is going to occur in this base map exercise geodatabase. I'm going to choose the feature dataset name. I'm going to call it Logan. Notice I'm not putting spaces in the name. Sometimes things go wrong when you put spaces in the name, so I found it's just safer not to, although it's getting a little bit more robust in terms of allowing that. Also, I don't want to use this Web Mercator coordinate system. I want to use a UTM coordinate system for this area because that preserves lengths and areas better. Remember, I was talking about coordinate systems last class. And you can see if you sort of pan around the map here at the bottom, it gives the coordinates. Latitude's around 40 degrees, the longitude is around 111 degrees west. You can actually work out, based on that 111, that we're in zone 12 of UTM, the Universal Transverse Mercator Coordinate System. And there's a bit of an explanation for that in the exercise on the bottom of page 6. Each UTM zone is 6 degrees wide, and the counting starts from 180 degrees west. So I'm going to click on this little globe next to the coordinate system and find UTM zone 12. It's a projected coordinate system, and somewhere down here I should see UTM. I can expand on that. We're going to use, it needs to specify a horizontal datum. When we talked about datums a bit last time, that's effectively the system that positions the coordinates in space. I'm going to expand the North American Datum 1983 set and find UTM Zone 12 and click on it and say OK. And now if I click Run, so whenever you've finished setting the parameters for a geoprocessing tool, you typically set Run, and then it'll take a few seconds to do whatever the task is associated with that processing tool. It's now finished, and I can click back on Catalog, and I see that there's a Little Bear Logan feature data set. A feature data set is indicated by this those three rectangles overlapping in the base map exercise. And we're going to assemble most of our work in there. So now I'm going to take this, let me just, now I'm going to select the Little Bear Logan watershed and copy it into that feature data set. To do that, I need to switch back to the map tab. This is on page 9. Sometimes this map tab will be active if you happen to be working with Explore, but in this case, the insert one was active, so you can switch between the ribbon tabs up at the top here. I'm going to find the select tool. I'm going to click on that, and if I click there, you'll see it changes this particular feature. So now this is only one of the 6 features within this feature class. And with that selected, any tools that I execute will run only on that. Let me get this pop-up here out of the way by closing it. And I can, with this feature selected, now following on page 11, so you can see you shouldn't have been intimidated by the fact that this thing was 45 pages long, because we're already at page 12 actually. I can right-click on WBD HU8, say I'm going to now export these features. I'm going to export them into the feature data set that I just created. So when I click on that, you'll see now it pops open a different geoprocessing tool that's a copy from a feature class to feature class. The input, it says, is WBD HUG8. The output location, now this is a place where you have to pay attention because we're not actually using the default. I'm going to click to browse, and rather than just putting it in the geodatabase, I'm going to put it inside the feature data set within that geodatabase. So click browse, open that geodatabase, click on the Little Bear Logan feature data set and say OK. So now that output location changes to Little Bear Logan, and if you click inside there, it'll show you the full path. It's Little Bear Logan, base map, exercise GDB, and then the earlier parts of the path. For the output feature class, I still need to give it a name. I'm just going to call this. This is the watershed that we're focusing our study on in this exercise, and I'm not going to worry about any of these other parameters. That I'm just going to leave them at their defaults, and I'm going to click to run, which you can see when I hover over run, it executes. It says execute the tool. So if I run on that, it takes a few seconds, and then it finishes. And what you'll see happened is that there's a new layer in my map called Watershed, and there's also, if I switch back to catalog, within Little Bear Logan, if I expand that, there is the watershed file geodatabase feature class. I can turn off, sometimes it's good to clear the selections, so get the selection. I could turn off the watershed boundary data set. You see, I've just isolated in on the watershed of interest. So that's going to be the boundary of our study area. And I'm not actually going to work with WBD HUC8 anymore, so I'm going to remove it. So now there's two actions that you have to be concerned with when working with ArcGIS. The remove is something that just decouples it from the map display. It doesn't actually change the data, so it's a safe sort of operation. So the remove will remove that layer from the table of contents here, but it will still exist on my disk and in whatever geodatabase it is. If, on the other hand, I went in there and did a right click and did delete, that would erase it from my disk. So that's a less safe operation. Now, sometimes you still want to do it. Well, it depends on, yeah. There's occasions where you have created things that either are erroneous or duplicate or you want to delete for whatever reason. In this case, I am going to be removing it, but it's good to know the difference between the concepts of remove and delete. So remove it, it's disappeared from my map table of contents, but it still exists over there. So now if we switch back to the Explore tool and click on this, it shows me similar information as before, the area in square kilometers that came from the National Hydrography Dataset, the same HUC8 identifier, but notice that shape length and shape area are much bigger numbers. This shape area is actually an area in square meters, and it's roughly 2,288 million square meters, which, if you divide by 10 to the 6, it corresponds very closely to the 2289 that we got from the USGS. So here we can see the area that ArcGIS is calculating when we're using the UTM coordinates is much better. And this change happened when we moved this feature from this geodatabase, the NHDPlus one that used latitude and longitude coordinates, into this feature data set that we set to be using UTM zone 12 coordinates. We can also change the map display to use our UTM zone 12 coordinates, and we do that by right-clicking on map here and going to properties, and there's quite a lot of properties of the map, and you can sort of flip through them all. But the one we're going to be interested in is coordinate system, and you'll see that it gives you an option to select the coordinate system and view the available options. Right now, it's using a geographic coordinate system, and you can tell that if you scroll up higher, it's in the geographic coordinate systems catalog for the North American datum of 1983. We actually want to use the UTM coordinate system, and we can expand this. It's really handy to have this layers group at the top, and you can expand that. And if I click on NAD 1983 UTM zone 12, that will say to pick the coordinate system from one of the layers on the map. This lists all the coordinate systems that belong to layers on the map. And the layers on this map are the watershed and my topographic base map, which is in the Swed-Mercator system, which is a system used by a lot of web map services. So if I click on that and say, OK, you see the map redraws, and it's now a little bit narrower. So, and that's because now the distances east, west, and north, south are no longer distorted, or no longer as distorted as when we were displaying things, treating latitude and longitude as though they were square. So it's good to periodically save your map project, because if my computer was to crash, I would have lost a few things. So I'm going to save the project up here. And we're about to transition on page 16 from the first part of the exercise, which was effectively opening an ArcGIS Pro project, to selecting Subwatersheds. So are there any questions at this stage? everybody following along? Okay, so I probably should have said at the beginning, if you've got ArcGIS and you want to try and follow along with me, you're certainly welcome to. If you just want to watch and then perhaps use the video recording to do the exercise yourself and stop and start as you go along, that's also often a useful technique. Let's see if there was anything in the chat there that I should. Somebody says they just lost. So, Merzinda Hell, do you want to tell me where you lost? You might have to turn your audio on. Okay, I'm not hearing from her, so hopefully she'll get in touch with me afterwards. So we got to page 16, and we're transitioning from the setting up the ArcGIS project and saving it to selecting the subwatersheds in the study area. So the subwatersheds are referred to as HUC 12. They're the HUC 12 level in the USGS hierarchy. So if I switch back to the map, and I find in my watershed boundary dataset, feature dataset, HUC 12, I can drag this onto my map just as I did previously, and you can see that there's now perhaps a few hundred polygons that represent the HUC 12 watersheds for this area. Let's look at the attribute table for that. So you can look at the attribute table. Each feature class has an attribute table that gives you information about every polygon. We saw that previously we could access some of that by just clicking and seeing the attributes for that single polygon. But if we look at the attribute table as a whole, that shows up on the bottom half of the map. Now you can see the table with all of the attributes, all of the columns. So there's, for example, things like a national map identifier, the date it was created, various area quantities, the area in square kilometers, the area in acres, the name, the associated states, the HUC 12 identifier, so that'll be the 12 digits that uniquely identifies each HUC 12. To HUC, this tells you where the downstream HUC. So there's a lot of connectivity here that's useful for tracing where water moves up and down in a watershed. There's a NHDPlus identifier, so this is a unique identifier associated with the NHDPlus system, and the shape area and shape length were computed from the geodatabase, and again in the latitude and longitude coordinates, so not very meaningful. We want to find the watersheds that belong to we want to find the subwatersheds that are at the level HUC 12 that belong to this watershed here. So if I bring this up on top, you'll see there's there, and we want to find all of those inside. This is a database selection function, and a lot of working with ArcGIS is using various querying and selecting to find things in a database. In this case, I'm going to select by attributes, and I'm going to do a query that the beginning of the HUC 12 identifier is the number that we identified for this HUC 8 watershed, the 160100203. So I can do a select by attributes that opens the select layer by attribute tool in my geoprocessing tab here. and I'm selecting things from the watershed. I don't actually want to select from watershed. I want to select from WBD HUC 12. This is going to be a new selection, and I need to build an expression for it. So I'm going to click New Expression, and I'm going to say where the HUC 12 identifier is not equal to something. Let me just make this a little bit bigger so you can see a bit more about what's going on. But begins with, so I can query part of that identifier, and I enter here 1601023, and now if I click Run, it'll run a query, and you see now it's highlighted a number of polygons. If I zoom out a little bit, you'll see it's highlighted all the ones inside of the green watershed I had, and some of the polygons, or some of the rows in this table, the ones associated with these selected ones, showed up. So there's a association between the polygon on the map and the polygon on the table. It's really useful if you want to find where something is on the map. You could actually select in the table and it'll show up on the map. There's a toggle down here that you can switch between showing just the selected records or showing all records, which was the initial default. So if I click to show selected records, it only shows the 27 of the total of 195 that were selected. So I could toggle back and forth like that. So now I'm going to use the same trick as I used before to put these in my feature data set. So let's right click on WBD HUC 12 and go to Data, Export Features. I'm going to again select my Little Bear Logan feature data set as the output location, and the output feature class. I'm going to look at my notes here to be consistent with what I was doing before. I'm going to use the name Subwatersheds, and that's on page 20. More than halfway, no, nearly halfway, not quite halfway. So now if I click Run, it's doing its work and says it completed. And if I switch over to catalog here, you'll see that there's now subwatersheds in my Little Bear Logan feature data set. And you can also see that there's a subwatersheds layer that showed up here. So if I remove this WBD HUC 12 layer, which I don't need anymore, I'll just have the subwatersheds for the HUC 8 I'm interested in. So now we're sort of starting to basically identify the information that we just need to work with in this watershed. I can click on, say, this one, the top right, and I can see that this is its particular identifier, and it's got a shape length and a shape area, again coming out of the geodatabase, 109 square kilometers, and the length, this is the length around the polygon, and it has the corresponding unique identifier. So this, the way to interpret this is and this is given on page 21. This is region 6, subregion 1, the 01, basin 02, subbasin 03, watershed 03, subwatershed, well, I guess it's 01 if I'm looking at this column, and subwatershed 04 is the one it drains to. I'm just pointing that out, but it's not something that I'm going to expect you to remember, but that's just the terminology that the USGS has come up with in terms of effectively representing this hierarchy of from large-scale regions to small-scale watersheds. So now I'm going to actually open the table for this set of subwatersheds, and now we've got only 27 records. So those were the 27 records that were imported into my geodatabase. And if I scroll to see the various columns, I'll see there's one for HUC 12. There's not one for HUC 10. But I might be interested in coloring this, for example, based on the HUC 10 watersheds, which are these watersheds here, but just dropping off the last two digits. So I'm going to do that for the purposes of also showing you how to manipulate data in these tables, add data to the tables, do some calculations with it, and that'll hopefully get your creative juices flowing about other useful things you might be able to do with data, working with tables and geodatabases. So there's a little button here that lets me add a field, and I'm going to call the field I'm adding HUC 10, because in this field I'm going to basically create a HUC 10 identifier by truncating these HUC 12 identifiers. I'm going to leave the data type as long. That just means it's a 64-bit integer to the computer. We don't need to worry too much about that. And to make this change that I've done stick, you actually have to click save at the top, because I've been editing a table, and this is going to save the modifications to the table. So there we go with that is now part of the table, and I can now close this detailed view of all of the properties of the individual fields in the table. And if I look back in just the table itself with the values, there's a new column on the right, HUC 10, and it doesn't have any data. All the values are null. So now we're going to do a calculation to fill it out. So this is on page 24. I'm going to right-click and calculate field. So this is the calculation, and this is actually a very powerful set of tools, and we might use it when we're calculating precipitation over a watershed, because you can do things like multiply the precipitation by the area. For example, you're using an area-based, say, decent polygon approach. In this case, I want to just effectively truncate the HUC 12 values. So because I did the right-click there, it opened this calculate field geoprocessing tool, and it says it's going to evaluate a Python expression. Python is a computer programming language that says HUC 10 equals, and I can put whatever I want in here, or if I want to put a longer block of code, I can type it in there. So I happen to know that this HUC 12 field is a text field, so I do int, which is the Python command to convert from text to an integer, and then I find this HUC 12, and I double-click it, and it inserts that in with exclamation points, bracketing, and that means it's pulling it from the fields here. I close the parentheses, and I divide by 100. So here I'm taking advantage of the computer's integer calculations, where when you divide by 100, it truncates. And this is a little line of effectively a computer instruction. It just looks like math. It happens to be the syntax for the Python language in this case. and I can execute that. And after it's completed, you can see that there's these numbers have filled in. You might want to actually make the field a bit bigger by dragging. It's a little bit tricky to drag it. Sometimes you drag it and the field sort of moves in a counterintuitive way, and I haven't quite figured out why it's doing that. But there it is. You'll see that there's these 10 digits that we just calculated there. And now to look at what they are, it's going to be, well, let's symbolize them. So let me put this table away. And over here on Subwatersheds, I'm going to right-click and say Symbology. Now, sometimes there's two ways you can get into the Symbology. One is you can just click on this, and the other time you can right-click here. If I just click on this, I get right into editing the symbol. But if I right-click there, I get to a higher level, and I can also get back by returning to the primary Symbology page. I actually want to start from the primary Symbology page because rather than having a single symbol, I want to use unique values to color this layer, and I'm going to use, rather than TNMID, I'm going to use this new HUC10 field that I just created. So now I see it's already filled in default colors for me, and I've symbolized this watershed, showing what we learn now is 4 HUC10 watersheds within the single HUC8 subbasin, and each of them have 6 or 7 HUC12 subwatersheds. So that's the sort of hierarchy that we have established for this area. So there's a nice display there with a sort of pastel shade that shows you the organization. Now, we may be interested in the area associated with each of these HUC10 watersheds. At least that's a question I'm posing to you guys. So anybody with any ideas how we could come up with those areas? Speak up if you just, I'll pause for a bit.
Are you talking about the areas of the individual watersheds?
The HUC10 watersheds, so the ones that are shaded in the pastel colors.
Can't you do the same thing, calculate just the area field instead?
Well, I could, but I guess I don't have a single object that represents them. If I actually look at the attribute table here, I have the area for the 27 subwatersheds in, for example, this shape area field represents in meters, but I have to identify all of the ones that have a single number, like this one, 16, that one, all of the ones that belong to with the same HUC10 code, and then I'm going to want to add those areas together. So you can see there I've been selecting a few of them, and in the map I'd have to select all of them and sum them up. There's a neat little trick, and I wanted to, part of the reason for asking that question was to show you that trick, to just illustrate some of the database type of work that can be done here. So I'm going to clear my selections and go back to this HUC10 field, and if I right-click and I go to summarize, so this is a summarize, a function that lets you summarize fields in your table based on other fields. So if I click summarize, and I believe this is on page 27, you'll see it's opened the summary statistics tool, and it says my input table is subwatersheds. It's going to output a table subwatershed statistics. The statistics field I'm interested in, let me say I'm interested in shape area. So maybe I'll go and click on shape area. And the statistic I want is a sum, and the case field is HUC10. So the case is what defines a separate case over which we want to sum. So there's a sort of interesting type of mathematical operation that's going to act on this table, sum together the shape areas that correspond to each of these, that correspond to whatever the HUC10 unique identifiers are. And a table will be produced that's named subwatershed statistics. So if I run that, I didn't pay attention to where that table is going, so it's probably just gone by default into the geodatabase. We can click there and see, yeah, it's just in the geodatabase. You see the table popped up here on my map, and I can open that table, and it's got 4 records identified by the HUC10, and it's got the sum of the shape areas. These sums are in square meters, and it actually also tells you the frequency, and the frequency tells you how many subwatersheds are in each of those watersheds. So we've summed up the areas over those 4 regions. That might be something that you need to do for some purposes, and if you need to do that, that would be a handy way to do that. Maybe you want to get this table and do some other calculations with it, and maybe you want to use Excel for that. So once you've got a table like this, you can actually just say export the table, and there's a number of options here. Before I do that, let me just go and get back into my base map exercise folder, and you can see the files that are there are still the same ones we had before. There's the project, the geodatabases we work with, but there's no comma separated variable file. I'm going to set the output location to be, rather than this feature data set, one of my folder locations. I'm going to actually pick the base map exercise folder, and I'm going to give the name for the output as Subwatershed stats.csv. So when you put the extension like that, ArcGIS actually interprets it and knows how to save the information. And if you wanted to learn some of those things that I'm just telling you right now, you could click on this question mark query, and it'll open the help information on. So it's gone to the ArcGIS website. It's opened the help information, and it's explaining all the gory details of that table conversion, saying it recognizes .csv, .tbf, or .dbf tables, and some other information about that. So I'm going to now run this tool, and we saw that it did actually put the subwatershed stats CSV table here, but more importantly for us, if we go to the folder, there's a subwatershed stats CSV table that I can now double click and work with in Excel. So there's sort of interoperability between ArcGIS and Excel, and you can do the usual calculations in Excel that you might be familiar with if you needed these areas. So what I've asked you on page 29, so on page 29 in the exercise, the first piece that I'm asking you to turn in, and that's to make a layout of this map with the HUC 10 areas illustrated with these colors, the HUC 12 subwatersheds delineated there, as well as the watershed boundary, and sort of annotate it nicely by switching to layout. So I'm not going to go through the full process of it, but I'm going to just go through the process of starting a new layout. You get to specify the size of paper that you want the layout to occur on, and then you can get to specify where there's a map that appears on that layout, and don't know why it didn't appear there. Okay, I guess I no, I have to add a new map into my. No, I'm not doing that. I'm forgetting how to do it. I shouldn't deviate from what was actually in the exercise. In the layout, I can somewhere insert this map into my layout, and then I can do things like add the legends, add captions, and if you follow in on the getting started with ArcGIS exercise, it'll explain to you how to add things to the layout. So the first thing that I want you to do is basically make this map look pretty by putting a caption on it, putting a north arrow and a scale bar. So we might choose a funky looking north arrow, and probably it wouldn't be quite so big on the map layout, but make the map look somewhat attractive, and then copy and paste that into your screen grab that into a Microsoft Word document, for example, and build up the solution to the exercise. And when you're done, turn that in on Canvas. So that's where we are at. Now we've gone all the way to, I believe, page 29 or 30. So any questions at this point?
I have a quick question.
Okay, go ahead.
When you are trying to calculate HUC 10 from HUC 12 and you wrote down the equation using the exclamation marks, can you just tell us again what those exclamation marks mean?
Okay, I believe they are used to delimit the fields in the. They used to delimit the characters, the name of a field in the database. But let me go back and see if I can show that to you again. So say I'm going to do a calculate field on that, which is what I was doing. It says HUC 10 equals, and I was doing int. The way I created that was I double-clicked HUC 12 here, and it inserted for me exclamation mark HUC 12 exclamation mark. So I think what it says is that what's between the exclamation marks is one of the fields coming from above. Otherwise, it could just treat HUC 12 as any old Python variable that might have a specific value. So that's the way I understand that syntax. And I closed the brackets and went divide by 100. And
okay, yeah, got it. Thank you.
I'm not going to do that calculation again because I've already done it. Anything else?
I think I missed how you got your map to the layout view.
Okay, so I went to, first I inserted a new layout, so I'll do that again, so I'll end up with two layouts. And then I clicked on map frame. So the map frame is the object that holds a map in a layout, and it's showing me the map frame choices I have. And I'm just going to click on, I'm not sure what the default extent is. Maybe this map has a default extent, but if I click on this one, it's obviously the one that I'm working. And then I drag with the crosshairs that appear, and then the map appears in the layout. And then I can sort of move it around.
Great, thanks.
Anything else? Okay, so there's a little bit on page 30 about, it says, where's my stuff? As you work with things in ArcGIS, especially if you're moving between computers, it's handy to know where the files you're working with are in case you want to make a backup or something like that. And in this case, they're all in this base map exercise folder. You'll see that we got the CSV file. There's the two geodatabase files. But that's not always apparent. You can sometimes add data from other locations. So let me just close this layout, close the subwatersheds table. Let me right-click on these subwatersheds and look at properties. And if you want to know where that's stored, you can go to the source tab here, and there it says this is where it's stored. Users, DTOB, documents, ArcGIS work, base map exercise GDB, and that's its feature class name, and it's in that feature data set. So there's other things that the source will tell you. For example, somewhere it might also tell you the coordinate system. Oh, yes, under source, you can also scroll down where it says spatial reference. It tells you that what the coordinate system is, transverse Mercator, that we set. So you can, by looking at the properties associated with a layer, which you get by right-clicking properties, you can see where things are and also other properties about that. You will see, and I've got written a little bit about this in the exercise with respect to the coordinate system. This particular coordinate system has what's known as an EPSG number of 26912. EPSG stands for the European Petroleum Survey Group that originally developed a registry of coordinate systems, and that's a well-known identifier, which means it's widely used, and that's what WKID stands for. If you want some arcane explanations of this jargon. So it's also handy to periodically save our project, so I will do that. So the next part of the exercise is to add the flow lines, which also come from NHD. So here I'm going to go back to catalog here and expand the geodatabase. The flow lines happen to be in hydrography, and there's a field NHD flow line, which I will again drag and drop onto my area. And now you'll see the flow lines extend over a much larger area than what I was dealing with. And if I turn off the base map, you can see them a bit more clearly. And they are color-coded according to their type. Let me zoom in somewhere around Logan and zoom in a little bit more, and let me also turn off the subwatersheds. So now I could, for example, look at this flow line that goes through First Dam, you see it's actually an artificial path going through this this dam that the folks from Logan will recognize as the dam just above the water lab called First Dam. And it's got various other attributes such as length and the reach coding that I was talking about last time. It does not have any information about flow. One of the things that the National Hydrography Dataset gives us is estimates of mean annual flow through various approaches that the USGS has developed, and they're in this table. So this is effectively the plus part of NHDPlus. You can actually get this data just NHD from the national map team at the USGS, and that won't come with flow data. But because in hydrology we're often interested in flow, we'll be using this NHDPlus EROM MA. EROM stands for, I wrote it down, Enhanced Runoff Model, and MA says that's mean annual values. So I'm just going to drag that. I could even drop it on my map or put it in amongst the standalone tables. And if you open this table, you will then, let's get this pop-up out of the way. You'll see that there's a whole number of columns in here that give things like the one we're going to be interested in is the flow estimate E gauge adjusted mean annual. So these are the gauge adjusted mean annual flows, and you'd have to go and look at the NHDPlus documentation to learn precisely what that means. For each of the reaches, they're not associated with this feature class yet, but they're associated with an NHDPlus ID, and we have to add them to that feature class using a database join function. So the way I do that is I can right click on NHD flow line and say join, add this join. Now what this is going to take is this, in this NHD flow line table, there's a field that's the unique identifier. I'm going to join this onto this enhanced runoff model table, and I'm also going to use NHDPlus identifier, and I'm going to run this tool, and now it's joined the one table onto the other. So when I click on the stream, I see a whole lot more attributes that were pulled in from this other table that I added, and the quantity that I'm going to be most interested in perhaps is the flow gauge adjusted mean annual flow of 248 CFS. So that's what this is telling me, is there's 248 CFS flows through First Dam on average, according to this estimate, which is based on geographic attributes. It's not directly measured. There is a gauge nearby, so it's pretty close to what that gauge is, but it's not an actual measurement. And there's estimates of these at all 2.7 million of these around the country. So now we want to, similar to what we did before, focus just on the flow lines within our watershed. So I'm going to now use a different type of selection. Last time we did a select by attributes, and I did a query based on the HUC identifier. Now I'm going to do a select by location. So I can do that select by location. I'm going to select features from NHD flowline that have their center in. So there's a lot of choices that you can choose here. Are completely within their boundary touches. I don't know what clemency is. You'd have to read the help to find out about that. But say they have their center in, and the selecting feature, I'm going to choose my watershed. I'm going to select all the features that are in my watershed, And I think that's all I need to do. So I'm going to run. So we see a lot of these flow lines showed blue, and I can right-click here and zoom to selection, and you can see it selected all of the streams that were within my watershed. It had their center within the watershed. So that's handy to effectively give me a subset of the flow lines, because I'm really only doing a study on this particular watershed, not this whole region. So now I want to again add those to my feature data set where I'm collecting information. So I'm going to do the same thing I did before. Do data, export the features. I'm going to put it in the Little Bear Logan feature data set, and I'm going to give it a name, flow lines. Very original naming system here. And now I'm going to run. So now it's actually doing quite a lot of things. It's only operating on the selected features. Because the selected features hold a table that's got a join to it, it's going to be copying the table values that are from the original flow lines table as well as the join table, and it's going to be putting them all in that feature data set. And it's also going to be converting the coordinates from the geographic coordinates into UTM coordinates. So there's a whole lot of stuff going on in the single command, and that's what I said at the bottom of page 36. So if I now clear the selection, say turn off the NHD flow lines, you can see here we've got the table of flow lines that's got added to the map. Maybe I want to see it a little bit bigger. And I could, for example, click on one of the reaches, see if I can get the same one. I didn't quite get the same one. But I can go and see, for example, what the estimated flow in that particular reach is. So this table is a whole lot bigger than what we were looking at. It's got a whole lot more columns or a whole lot more fields than what we were looking at before. So one of the handy things to do with this is to be able to symbolize this information with using mean annual flow to represent the width of the streams. So I'm going to use I'm going to adjust my symbology for that. So I'm going to go to flow lines, open the symbology, and rather than single symbol, now I'm going to work with a graduated symbol, and I'm going to select the field that I want to do the gradations on, and I'm going to pick my flow field. So the gauge adjusted mean annual flow, and we're using flow estimate E, gauge adjusted mean annual flow. And you'll see that, well, the color scheme is not really good. So if I switch the color to a blue, which is more typical for rivers, you can see that it's shown, I guess if I go back there, it's come up with different widths for the different ranges here. And you could actually fiddle and edit these values if you wanted round numbers there. But you can see we've shown the main stream as sort of getting fatter as the flow gets bigger. So this is a very nice visualization of what the estimated flow in the Logan River is, the Blacksmith Fork River, the Little Bear River. So that's pretty cool. So this is the next thing I wanted you to hand in, is to make a layout that shows that and sort of symbolizes with these includes a legend that shows how to interpret these widths in terms of mean annual flow. So we see we're getting down to right where this leaves our study area. We've got mean annual flows of about 500 CFS. Now, one of the weaknesses of ArcGIS is that we don't actually know what these units are from the system. We have to be reading the documentation to learn that. It doesn't keep track of units. I find that a limitation, but the argument could be made that Excel doesn't keep track of units by itself either. You have to keep track of the units in many calculation systems. So the last thing I want to do in this exercise is add some stream gauges. So if you look at page 39 in the paper, in the exercise, you'll see that I've given a table where there's latitude and longitude values for 3 stream gauges in this watershed, as well as the mean annual flow, the drainage area in square miles, and the latitude and longitude are specified in degrees, minutes, and seconds. What I'm expecting you to do is take that data and split it out into degrees, minutes, and seconds, and then calculate the decimal degrees. I've done part of the calculation already in preparing for this in this spreadsheet. So here I've got the data from that table where there's the site identifiers, the site names, the latitude and longitude, and then I expanded out latitude, degrees, minutes, seconds, longitude, degrees, minutes, seconds. And I'm going to add a new column that's latitude, decimal degrees, longitude, decimal degrees, and then here I'm going to do the calculation of latitude as this, the latitude plus the minutes divided by 60 plus the seconds divided by 3600, and I'm going to copy that down. So those are the latitudes in decimal degrees for all of these locations. The longitude is a little bit more tricky because we're west. So you have to put a minus number, and you take the minus the longitude in degrees plus the longitude in minutes divided by 60 plus the longitude in seconds divided by 3600. And if I copy those formulas down, I've evaluated longitude. Make sure that you've got these columns wide enough that you're showing 5 or more sort of significant figures, because it's actually going to use those number of significant figures to position those points precisely, and with fewer than that points you can get sort of imprecision in where the things are located. I'm going to save this file as a comma-separated variable file. So, and that's because that's what's easy to import into ArcGIS. So I'm going to go into my base map exercise folder, tell it I want to save a comma delimited file. I'm going to name it gages.csv and click save. And then I'm going to switch back to ArcMap and add data. And it doesn't appear there immediately. Sometimes you have to do a refresh. And there's the gages.csv. I can add that. And there I see at the bottom left here, I've got this this table that I just calculated in Excel, and there's latitude and decimal degrees and longitude and decimal degrees. So what I'm showing you here is actually positioning, effectively creating data on the map. Maybe these could have been your house addresses or your study plots or something like that. I'm going to display them on the map using the display XY data tool, which opens the table to point tool. This is the input table, the output feature class. I'm going to put in my feature data set and call it gages. So here we're building up flow lines, subwatersheds, watersheds, gages, all the sort of base data one might need for a hydrologic study. And the X I want to get from the decimal degree longitude. The Y I want to get from the decimal degree latitude. If I didn't do that, I might get those gauges in the wrong location. And the coordinate system. Now you need to actually know what coordinate system was used to encode these values. And you don't know it, but I do, because when I downloaded this data from the USGS, it said it was with respect to the North American datum of 1927. So I'm going to go and find the North America, USA and Territories, North American datum of 1927 coordinate system. So it says GCS North American 1927. So that's the coordinate system I'm going to use. It won't be too far wrong if you do something else, but it's better to use the one that is actually right. And I click Run, and now there's 3 dots. You don't see them very clearly, but if I change the symbology to perhaps a circle with a dot, and maybe make it a sort of a bright green. Those are the stream gauges. So let me get the table out of the way, and you can see there are the stream gauges that we entered the data for next to the streams. And I think I'm asking you to, at the end of the exercise, to make a layout that shows the streams and the stream gauges labeled. So you can label these by just right-clicking on gauges here, and there's a label option, and it's put the labels that came out of the name field there. Now you can also go to the label properties if you want to change the font, perhaps make it bigger or something like that. So I've asked you to label these, and also to zoom in and say we zoom right in there. We can click on this one, so you can see it's not located precisely next to the stream, so maybe the latitude and longitude is not that precise. But if I click on this, you can see that this has got a drainage area of 214 square miles. The mean annual flow is 238 CFS. If I click on the stream that flows by, you'll see that the gauge adjusted mean annual flow is 270. So those are not precisely the same, but they may be for different periods of records. Plus, this gauge adjusted mean annual flow is based on a regression on watershed attributes. So I've asked you to just make a table of the gauge adjusted mean annual flow and the flow from the gauges. You can do that just by sort of clicking and writing down the numbers to see how close they come out. We saw that they came out to within about 40 CFS at this location. And you can find out by sort of zooming out and going and clicking at the other gauges what the values are there. So what you're seeing there is how things that are geographically located, you can use the GIS to learn information about it, and then learn information about a nearby location, and sort of derive some sort of knowledge about at least how good these streamflow estimates are in comparison to measurements. So that was all that I had for this exercise. There's just those 4 few things that you should be able to work out and hand in on this part 2, making the 3 layouts and the table comparing the gauge mean annual flow and the NHDPlus mean annual flow. So I'm going to pause there and bring up the GoToMeeting chat and see if there's any questions.
I have a question. We were doing the join command. If you mess that up, can you like rewrite it? Because I clicked on the wrong field and it didn't. It like gave me a bunch of nulls because I clicked on the wrong field. But is there a way to overwrite that if you screw it up, or do you have to like reload everything?
There is a way. So you can right click on the layer, and under joins and relates, there's a remove all joins.
Okay. So you have to remove them before you go and do it over.
Remove those joins and then add back the correct one.
Okay, thank you.
I believe you might also be able to just, if there's only one join, or if there's multiple joins and you remove, you can have multiple joins. If you remove, you may be able to selectively remove them, but remove all joins will get rid of all of your mistakes. And it tells you, are you sure? Any other questions? Okay, well, this exercise is due 1 week. So in general, I'm going to allow a week for you to do these. If you run into any difficulties, feel free to email me or contact me on Canvas, and I'll do my best to answer. And if it turns out we're having common problems, I'll email the results to everybody or cover it at the beginning of next class.
Question.
Go ahead.
Is it all right if are we required to do this assignment on the Little Bear Logan River, or are we welcome to do it on a watershed that's more relevant to our work?
You're welcome to do it on a watershed that's more relevant to your work.
Thank you.
But then you'll have to, for yourself, you'll have to find some stream gauges and some attribute values. So if you know how to do that, you're in good shape. And you're also going to have to find, you'll have to find which USGS region your watershed's in and load the appropriate data from the national map.
That makes sense. Thank you.
Any other questions? Okay, well, thank you, and talk to you guys all on Tuesday, and perhaps by email before then. I'm going to stop the recording.